So I'm going to start out with recommenders, topics, and text. So this prize, this Netflix prize, actually was a real inspiration for the machine learning literature on recommender systems. All of you have probably heard about it. It was this prize, $1 million if you could beat the Netflix recommender system. They published some data, 480,000 users, 18,000 movies. There were 100 million observed ratings, but that meant that there was a very sparse matrix. Most people had not rated most movies, okay? And so that's the classic recommender system problem. Again, one of the first observations, and I actually want to, maybe I'll pause for a little philosophy on this too. Hito said, any contest is always won by the average of hundreds of models. So when talking to people like Hal Varian and Pat Byery about what were some of the first things that they sort of learned when working with machine learning people on real-world big data problems, it was that model averaging was just amazingly powerful. And actually, it's kind of upsetting for us, right? Because we all thought that we knew something about the world. And if you had an economist came in and tried to predict, people buying stuff, that we would do a better job than just throw in a bunch of models and stuff, right? And the fact that an average of 600 models beats any structural model is kind of depressing. But we should remember actually what they're trying to do here. And this is going to be a theme that I pick up later. They are trying to predict in a stable environment. They have a stochastic process, and they're trying to predict when nothing changes. They are expressly, out of sample prediction is not counterfactual prediction. Out of sample prediction is I take 10% of my observations, but the joint distribution of the x's and y's and the 10% I pulled out is exactly the same as in my training sample. So it's just about kind of functional form fit. It has nothing to do with what would happen if Amazon changed their pricing policies, right? So the fact that we always lose at prediction is not actually saying that what we do isn't important. And in fact, we know that, I hope not. I would say that we know that actually from IV, because of course when we run an OLS regression, that's the best linear predictor, but when we do IV, we reduce our goodness of fit to get a causal parameter, okay? So our goal has never been goodness of fit, and that's really a difference. Now I will say that actually what we learn, we can often decompose our problems to where prediction is a part of it. And then, once it's the pure prediction component, their techniques beat ours. So we should change what we do. If we're trying to predict, they have better techniques. Boom. But that doesn't mean that's all we do. That's only part of what we do. Okay, so Netflix challenge. It inspired a lot more research. There was already a lot of research. There are whole books on recommender systems. And then those books only cover part of the literature. So this is also a really, really hard literature to wrap your head around. So I've wrapped my head around part of it, but I'll try to tell you about it. So recommending systems, basically you're trying to predict whether a user will like an item or how much. So actually in the Netflix challenge data, it was like a bunch of question marks. You hadn't rated them, and then what you did rate, you rated 1 to 5. Here, just for simplicity, I'm going to think about a setting where you have a big matrix of zeros and ones. So 1 is if you clicked on something or you liked something. The zeros could be because you were never exposed to it or because you were exposed to it and you didn't like it. I'm going to just put that aside, okay? But that's basically what it is. So actually, there's a lot of this literature that works on the idea that you don't have any item characteristics. So all I know is that there's a bunch of people, and these are the news articles they read or the web pages they clicked on, but I don't know any attributes. So I'm just going to try to make predictions based on a big matrix of zeros and ones. And then there's another part of the literature that works off of the observable characteristics. Okay. So obviously, this looks very much like discrete choice modeling, right? We're going to try to predict if somebody's going to click on something. We think that's something we know something about. One of the big differences here is that there's multiple choices per user. And so actually, I would say there is a very small economics literature on discrete choice that focuses on multiple choices per user. So there's like a political economy one about you take people's voting records and you look at their choices of how to vote over, and they have lots and lots of different things they vote on. There's also a literature, a very small literature, but kind of a marketing literature where you look at Nielsen data and somebody's looked at multiple movies. But that's not been the main focus of the IO literature on discrete choice, and this multiple choice issue is the typical case in their literature. It's massive. There's lots of disconnected subliteratures. I would say that, for economic applications, machine learning methods have a lot of promise for large-scale discrete choice modeling, but there's more work to be done to tailor them to our tastes. And so one strand I'm collaborating with, and I'll show you some notes later, from David Bly. He works on topic modeling. There's a group of people in computer science that build latent variable models. And those models look a lot like our structural models. And so I think, but they actually compute where ours choke. So that's something that I'm working on. Okay. So one thing that can be kind of especially confusing here is supervised versus unsupervised learning. Because actually some of the methods, the same methods are used for both, and that can make things very confusing. Let me just remind you again, Hito kind of made this clear before, but let me just repeat. Supervised learning is when you have a y and some x's. Unsupervised learning is when you just have x's, okay? So unsupervised learning is like, I've got a bunch of videos, I don't have any human labels, I don't know any names of what they are, I put them into groups. So when you do it on videos, you find a group of videos that all look similar on YouTube, and then when you actually watch the videos, some of them are cats. And then if you're lucky, somebody writes up in the New York Times that these smart computer scientists have found cats on YouTube. And if you ever wondered what that meant, how could there be a science to find cats on YouTube? Like, I think my toddler can do that. What they mean is that they put all the videos on YouTube in a bunch of clusters, and instead of having all those be videos about different things, it actually worked. What does it mean that it worked? It means that all the videos in this cluster were about cats, okay? So that's what unsupervised learning is about. So the unsupervised version of recommendation would just be that, like, I have a bunch of documents, and I'm going to put them into clusters and somehow say that some things are similar. And then later on, if I want to recommend them a book, I'm just going to look at what books are similar to the books they've read before, and I'm going to recommend those books. So it doesn't actually use the choice data. It's just finding similar things. And so I just want to mention, I'll come back to this later, but you might ask, like, as an economist, we usually think about incorporating all the information, like we especially structural modeling people want to use sort of all the information in the data. So you might wonder, why would I ever want to break my problem into two parts? First, look at similar things, and then maybe feed that into a model later. And I just want to say that actually in a lot of my applications, that's exactly what I want to do. Why? Well, if you use choice data and item attributes to put things into clusters to say, then what you're going to do is you might find two books being similar, that people like them together. So you'd say these books must be similar. But in fact, it could just be that Amazon's recommendation algorithm in the past always put those books together, or always put them on the same page. So people chose them because Amazon put them together. Or somehow the New York Times would always have three things, one sports, one news, one business in the top. So people often read one sports, one news, one business. That's not what the people liked. It's just that's the way the New York Times presented it. And then if you wanted to ask the New York Times, should I rearrange your web page? Well, you might say, if you use the choice data, you would say, oh gosh, yes, you should always have one sports, one news, one business, because that's what people like. But it's not what people like. It's just what you did in the past. So it can be helpful sometimes to decouple grouping things into categories from the context, unless you've been really careful about controlling for the context when you do your estimation. So then the supervised part is where you would use people's choices to make predictions and possibly put things into groups. And so those are two separate sets of data, but confusingly, sometimes you would use the same methods for both because you're decomposing matrices. Okay? And then there's these hierarchical and graphical models, which I'll come back to, which are more structural models, if you like. So the basic thing is that you've got this data set, and I think it's actually really useful to just think about the world this way for a second. Your data, roughly, is like a big matrix. And so if you're going to project that onto a model, it's going to be some way of simplifying that matrix. And a lot of methods may seem very different at the outset, but ultimately it's about taking that matrix and finding a simpler way to capture its information. Okay? One other thing I'll come back to is that this matrix can also be represented as a network, like users are friends with items and so on. And also there are techniques from the network literature that can be used to analyze matrices like this. So in this case, the goal is, like, say, to predict probabilities that users choose items. So I might say, this is my input data, and I want to predict whether I've seen some users have have evaluated this item. Maybe other users have never been exposed to this item, and I want to predict the probability that they'll like the item. If it's a very, very sparse matrix, I might also say that if there is 0, you know, I might still be interested in the probability they would like that item because just maybe they've never been exposed to it. Okay, and again, with the Netflix challenge, actually, there's an issue of things not being rated at all and ratings 1 to 5, but let's just stick with the 0s and 1s. Okay, so collaborative filtering is basically, the first connection is this is a classification problem, or that is, this is a discrete choice problem. And so the very simplest thing you could do is you could go back item by item, okay, so book by book, article by article, and I'll do a separate logit model for each one of those things. And what are my covariates? It's just indicators for everything else you liked, okay? So just, you know, thinking here, if I wanted to, here's my user, I'm trying to predict this, I can put indicators for everything else that I liked and try to predict. And so this guy liked this item, and he also liked these other things, so I would put positive coefficients on those other things that he liked, okay? So nothing wrong with this really, except for it just doesn't work very well if you have very sparse, very high-dimensional matrices. And so what you want to do is end up combining those with some other methods to reduce the dimensionality of the feature set if you even wanted to attempt to make it work in very large things. And also just this item-by-item prediction is costly. Okay. So another very popular approach is k-nearest neighbor prediction, or KNN, and it's you know, quite widely used as well. So basically what I'm going to do is first I'm going to take every item and compute its similarity with every other item, okay? And then if I want to make a prediction, I just find the most similar items, and I'm going to average the user's preferences over those similar items. And maybe I'll do that in a weighted average. No. So the similarity would be, so this is what's interesting about, you can turn your head a lot of different ways in the matrix. So even with just this data, each item is going to have a vector of user preferences. So I'm going to, even without item characteristics, I'm going to be able to say one item is similar to another item if users like those in common, okay? And so the way that you actually implement this is you take the cosine angle distance between the two vectors. So you can just think of these vectors like they're in, you know, in three-dimensional space. You know, there's 0, 1, 1 is a vector, but in higher dimensional space, you can still take the angle distance between two vectors, and that's how similar they are. Okay? So this is also, you know, commonly used, and actually these cosine distances are used in text mining as well, in relevance measurement for search engines and so on. But so it's very easy, very fast, and sort of like nearest neighbor matching, we kind of understand what it is. We're not making a lot of model assumptions, so that's attractive. The problem is that if you have a very sparse matrix, you're going to predict a lot of zeros. So if I've only, you know, clicked on 5 web pages and there's 100,000 web pages to click on, then, you know, one web page might have, you know, 100 nearest neighbors, but I've never clicked on any of them. So I'm going to get a lot of zeros. And so that's you know, that's a disadvantage. Then it also, there's a whole literature on doing weighted nearest neighbor matching where you estimate weights. But I would say at that point, once you're going to estimate a model for those weights, maybe there's other models you could estimate that might work better. So, but really, as I mentioned before, you know, this problem of matrix reduction can be broken down into something quite simple. What we can really think is we've got this matrix and we're trying to find similar things. So one way to do it is to posit that there exists some set of factors, some smaller set of underlying factors. This is a little bit like principal components, except I'm going to break this 2 ways here. I'm going to start with this big matrix. I'm just going to make up a number k. Say I like 10. I want to have 10 factors. Okay, I'll make that up. And I'm going to posit that this can be written as the product of user factors times item factors. And so you can just think of decomposing the probability that user I likes choice j is user's I preference for factor k and item j's weighting on factor k. Okay? And so this feels a little bit more like a structural model, and it would have some interpretability. So the easiest methods for this is that there's just, you know, these nice, fast, scalable computer science methods for minimizing the mean squared error of the predictions. So once you pick k, you can find those 2 matrices that minimize the mean squared error. So the nice thing about this is that you don't have to optimize anything, nothing, there's no converging, there's no like complicated priors to write down. You just pick a K and there's built-in routines and it goes to town. And then what comes out, you might already be able to gain some intuition for. So I'd say this is really good to just to start describing your data and understand what's going on. The cons with this is that because there's no model, it's hard to sort of enrich your model. So it's hard to start adding covariates in. In some of my work on news choice, I want to control for whether you were at a news aggregator or what was your choice that might be changing. There's lots of things I might want to bring in, and this model is not so easily extensible. But I think it's nice to sort of start with this because we're going to talk about some more complex factor models with all these priors and stuff going on, but ultimately they're kind of boiling down to this. Like this is sort of the information that's in the data. There's a question of how we estimate it and how we do inference and so on. Okay, so there's a bunch of other approaches that basically build off of the unsupervised clustering methods that Hito already talked about. And you can use any of those methods and as your sort of component methods, but iterative clustering, basically what you do is you take any of a variety of unsupervised methods to find, say, groups of similar items. So you have 100,000 items, and now I put them into 10,000 groups. And then I say, all right, now I'm going to find groups of users who like similar groups of items. And so I turn my head the other way, and I cluster the users according to which groups of items they like. Then you turn your head back, and you further reduce the dimensionality of your item groups, and you keep going until you have some smaller set of groups. And that's going to look, I mean, the result is actually going to look similar to this in the sense that you're going to have, different groups, or it's kind of like decomposing things into factors, but it's a different approach to it. And then lastly, there's structural or hierarchical models, which specify the latent factors and the distributions they're drawn from. So you might, again, actually start and say, I posit that there are K factors, but I'm now going to say they have a prior distribution, and I'm going to model that distribution, and I'm going to estimate things, and when I come out the other side, I'm going to have standard errors and such like that. So I'm going to come back to some examples of how that's done in machine learning after a little digression. So I'm first going to talk about documents. So this is sort of confusing, so I just want to warn you it's confusing, but hopefully that will save confusion later. So I started talking about a big matrix of zeros and ones where users chose items. You can also have another big matrix of zeros and ones, but now I have documents and words that are in the documents. So what I do is I actually create a dictionary of the most important words in the English language and the most important bigrams, that's pairs of words in the English language. And then my data then becomes, I've got documents, and there's zeros and ones if those unigrams and bigrams were in the data. And actually, Hito was talking about millions of right-hand side variables. For click prediction and search, there's actually billions of right-hand side variables because there's a freaking indicator variable for like every bigram, every pair of words, and the cross product, an indicator variable for this pair of words in the ad and this pair of words in the user query. That's all the indicator. That's a lot of right-hand side variables. So anyway, so that's a very common issue. You've just got a very sparse matrix of zeros and ones for whether words are or are not in a document. And so for understanding and grouping text, your goal might be to put the documents into topics with similar collections of words. But actually, from a prediction perspective or a mathematical perspective, these problems are very similar, and so a lot of the same methods can be used. All the clustering methods, unsupervised methods. So to find topics of articles, you could use any unsupervised method to put the documents into clusters in terms of their similarity of their vectors of their word presence vectors. Or you can use hierarchical models that I'll talk about in a minute. You could also just use classification. And actually, for the economists who have classified text so far, that's mostly what they've done. They've run a classifier to say whether an article is positive or negative review or whether it's left or right political bias. So you're running a classifier like a logit or an SVM or a classification tree to predict which side you're on using labels, like human labels for a subset that said that whether they were left or right, and predict which way they are. Okay. So so how do you classify documents into groups or whether they're politically biased or whatever? You take the articles, you have humans label as many as you can afford, and I've used Mechanical Turk for this, so the great thing about Mechanical Turk is you can put it up in the morning, and in the evening, you have a couple thousand things labeled. That's a very fast in my research world, since everything else seems to take much longer. So very easy to do. And then you build a classifier to classify the unlabeled articles. There's a fast version that some people that used to be at Yahoo or now at Microsoft Research have online, Valpal Wabbit. There's a lot of other ones. You could use Lasso, any of the supervised methods for classification. There I'll just caution you, if you actually see somebody give a seminar about this, they make it look really easy. Like, oh, it was great, the machine just did this. And we kind of emphasized earlier doing these things without human intervention. If you actually want a really good classifier of whether whether news articles are, have lots of emotion in them or something, it's darn hard to get them to really work well, and you actually have to spend a lot of time with your features, and it can really matter which method you use. So it's not quite as easy as it looks. So I'll just mention something that I've done in work that I've been doing with Marcus Mobius and Yeno Pao on that tried to sort of grapple with the fact that classifiers don't work as well as you would like. What we did was we used unsupervised learning prior to human labeling. So we took all the news out there, and then we used unsupervised learning to put the articles into topics. And then some of those topics turn out to be like tornadoes or sports events or something else. If we were interested in political bias, then we can say, we don't actually have to measure political bias for things that have nothing to do with politics. So by pre-classifying the articles, we could really conserve our human judging resources. In addition, some things about the articles can actually be judged by the topic as a whole. Like you could ask whether the topic is generally one that's emotionally charged or one that might be ethically controversial. So you can ask that question about a whole topic. But then because I can actually very, very effectively classify whether this article is about this tornado, and then the humans told me this tornado topic is say, not one that's ethically challenged, then I've actually know very well about thousands of articles all in one go, instead of paying thousands of Mechanical Turk workers to all waste their time telling me that this particular article, which was about a tornado, is not politically biased, right? So this combination really saved a lot of effort. So another approach to clustering is to interpret this word matrix as a network. And there's this whole other completely disconnected literature about network analysis that is sometimes applied here. There are network methods called community detection algorithms. And they were designed to find cliques of people who talk to each other, but they also work well for finding cliques of things that are like each other. Okay? So what we did is we applied that to the news articles, and we said the strength of a length between an article is determined by common words, as well as by links to common Wikipedia articles. And then I structured it as a network, and then trying to find communities. Now, in principle, a latent variables model should have found that. But basically, you can think of what we did was we imposed a whole bunch of structure on what was important. And because we were right, we did better than letting the data find the structure. This is another kind of theme. Part of machine learning says, oh, just throw all the variables in, and it won't matter, and the data will find it. But that's not quite true. It still matters how you put the variables in. And if you have an assumption that's right, like the model is linear and not a step function or something like that, you can actually massively improve your performance. So there's still a role for domain knowledge in actually thinking about your specification, even in machine learning models. So just as an example of how this worked, we created links between all the articles based, again, on their common words and whether they match the same Wikipedia article. And we discovered in the data a community or a clique of articles that were all highly connected to each other that were about President Obama's prom night. So I wouldn't have thought to look for that, but I didn't discover cats, I discovered President Obama's prom night. Aren't I clever? Okay. But that worked to kind of pre-classify these into topics. Again, then I could ask my humans, is President Obama's prom night politically charged or ethically controversial? And get ratings about all of the articles in one go. So these are some of the topics that we discovered in this thing, the NFL season, Ariel Castro kidnappings, a tornado, death of Lee Rigsby, and so on. Okay, so now let me talk a little bit more about hierarchical models. In some ways, these are closer to structural models, and really the differences are that the people who write them down are not thinking about out-of-sample counterfactual prediction. They're just thinking about prediction. but they happen to be writing down interpretable models, so they're closer to us. And it turns out they're just better at computing them on large data sets than most of us are. And so I think these are interesting to highlight, even though they're maybe a smaller part of the literature because they have more connection to us. So this is my co-author, David Bly, has done a bunch of tutorials on this. He has great material on his website that you can look at. I stole some slides from him. There's something called Latent dirichlet allocation, LDA, and this is a fairly popular method. And so what David has got specific implementations of this method that compute very well. So you basically say, I'm going to think about taking documents and put them into topics. Each topic is defined as a distribution over words. Each document is a mixture of corpus-wide topics, and each word is drawn from one of those topics. Okay, and I think my data generating process is that I'm going to my document is going to draw proportions of topics, and then I'm going to draw words that have each topic has a word distribution. So you can write this down, and this starts to look, at least in the equation form, it starts to look like a structural model that we would be familiar with. And you can just think about, given the observed data about words and so on, what's the posterior distribution over parameters. The way the computer science people like to write this down, they call them graphical models or hierarchical models. And in some sense, it's just like a Bayesian model. It doesn't mean anything to call it be graphical or hierarchical. It's just a model. It's just that they don't usually use models. So when they have them, they're graphical, I guess. So this is a graphical representation of the Bayesian model. The words are all that observed, and then there's these latent variables, and you try to use the data to estimate the underlying latent parameters. And there's a whole bunch of methods for estimating those things. The ones that Gibbs sampling looks a lot like the way we would do Bayesian estimation, but they have a whole bunch of other stuff that isn't normally used in economics. And I don't really know exactly how to evaluate those other methods. So David ran this on all the articles from Science and found a bunch of topics. And so these are some topics, and then the most frequently found words in those topics. So it discovers things about DNA, gene sequences, and so on. Those are collections of articles in Science on a similar topic. So again, as I mentioned this earlier, but just to reiterate, we actually have to think fairly carefully about whether you want to stop here. So this is just using the articles to find topics, or whether you actually want your estimation to incorporate choice data. And so the advantage of incorporating user choice data is that you're going to get a better prediction in a stable environment. So if I'm going to keep using the same way of people finding articles, if I incorporate what they chose, I'm going to do a better job predicting what they should choose in the future, rather than just using data about what's in the documents. But if I think I'm going to change the context or change the interface or change the way I do recommendations, it might be better just to decide if the two articles are in the same topic using only their exogenous characteristics. Another way to think about this is that from an econometrics point of view, we all kind of know if we take exogenous variables and recombine them in any way, we can still put them on a right side of the regression and we haven't screwed it up. But if we use the x's and the y's together in some complicated way and then put them on the right-hand side of a regression, well, God knows what we did, right? And so, it can be sometimes useful to decouple these things. But if you just want to make good recommendations, then you should incorporate the choice data. So actually, let me skip over that. So here's just an example of that. So he's classifying academic articles, and so David classifies the article about the EM algorithm as a statistics article. But then he looks at who's actually citing and reading these articles, and that data actually tells him that people in the field of vision really like the EM algorithm. Okay? Somehow in the vision literature, it turns out that using latent variable models and estimating with the EM algorithm really works. So people who read about vision also like the EM algorithm. So then you recommend this article both to statisticians but also to vision people. Okay. So this is a graphical representation of the latent variable model that incorporates the user data as well as the document data. So this is the article component, the topic component, and the user preference component. The only things that are observed are the words in the documents and what the users chose. But then you build a structural model around it, and you say that there's these components of topics, and that's going to tell us the probability that the words are in the topics. And then I'm going to take each document, and the documents are D, and I'm going to classify them in topics. and then the users are going to have latent preferences for those topics, and I'm going to have a structural model that incorporates all of those things. Okay? And they're going to estimate it using various methods. So just to conclude here, I would say this literature is one that I think we are going to interact with because it's very close to what we do. And when economists work with big data, one of the big things we're going to be asked to do is help make better recommendations, better predictions, and so on. That's fundamentally an economic problem. So we do need to learn about this. This literature has a couple of different areas. One has a whole bunch of quick and dirty techniques that can actually be a substitute for more complex modeling. The clustering methods, the community detection algorithms are built into R. You can just run them. So, in an hour, you can look at your data and have decomposed it into latent factors or put it into communities and have something to look at and think about. But if you want to get fancier and also have something that's closer to structural econometrics, you might want to learn a little bit more about these graphical models, latent variable models, to help understand what can actually be estimated. They do not focus on identifiability at all. So, like, God knows if you have, how much functional form is working and how much is actually identified in the data. So just like the structural literature in economics at first was happy with functional form assumptions and didn't care about identifiability, and ultimately evolved to think much more sophisticated about identifiability and the role of functional forms. That evolution hasn't really happened in this literature yet. So just say, what do I think comes next? So just in my own work about recommending news and thinking about people's choices of news, other things this literature has left out, besides the link to structural models, is trying to incorporate more about choice sets and the role of the intermediaries in determining what you choose. So, Netflix only showed you certain movies. That's why you never rated them. So trying to incorporate a little bit more about that kind of context, which I personally think is a really important economic question, just the role of these aggregators and intermediaries in determining what you buy, what you read, what you know, how you feel, who your friends are, Facebook, and so on. So that's a direction, this choice set direction hasn't really been explored. Okay, so let's see, how am I doing here? Okay, good. So I'm now going to switch to my second set of slides for those of you who downloaded them. So as I mentioned, pretty much still everything I told you before was, and that Hito told you, was about applying machine learning methods off the shelf. So we've saved you 30 hours of viewing something on Coursera, plus given you some economic perspective about how to think about it. Now I'm going to shift gears to thinking more about modifying those methods and what they don't do well. So I've actually kind of said a fair bit of this already, but again, I want to kind of hammer some of these points home, that supervised machine learning is great at non-parametric prediction with big data. It's got these great focus on cross-validation for model selection, and if you take only a few things away, my view is that we should all be doing that. That's what Lasso does. It's determining how many variables go in the model using the data, rather than pretending that God told you that or economic theory told you that economic theory told you should have a dummy for 60 to 68-year-old men in Alabama, and that's why the dummy's in there. No, economic theory didn't tell you that. That's a descriptive part of the model, and data should really be guiding us there. So I'm a big believer in that. Another kind of just philosophical observation is that this literature, the strength and weakness is that basically anything that works at prediction is okay. And so it's actually interesting from a scientific perspective. If you give a literature just one goal, which is to predict out of sample, and it's something that people can test, like just test. If you have a data set, you can just test if it predicts out of sample. And you have no other rules. That literature is really going to advance, right? I can write a paper like in an hour if I have an idea, step 1, 2, 3, 4, then I have to code it up, and if it works, it works. So that they really advances. And so that's really just one way to think about why it's so good at what it does, but just to remember that it's had a single focus. And actually my co-author, David Bly, kind of talks about, he does these topic models that are interpretable, and he sort of complained that there wasn't really a language in computer science for the benefit of interpretability. But we know the benefit of interpretability. If a model is interpretable, it's probably also likely to do well when the world changes fundamentally. And so we have a language for that, and they don't. And that's actually a really kind of a big advantage of us. Now there's a small literature on causality. Judea Pearl has whole books on this, and there's actually a large literature following him. They, instead of writing equations, they write boxes and arrows that show relationships. But their empirical literature has not focused on the same things we focused on. So one way to think about what it's good at is that suppose you have a huge engineering system, and there's you don't understand it at all. It's like software that's developed over years. But actually, buried in that software are rules, like this comes before this. And this is an input to that. And what comes out of this could never influence some other component of the model. Just technically, there's no communication between them. But there's so many of these things that I don't really understand them anymore. So you could get data from that system and learn the arrows. You can learn whether this thing influences that thing and that thing influences this thing. So we haven't really tried to do that because in most of our data sets, God, if we have one exogenous thing, we're happy. You know, we don't think we're going to find 100 exogenous things in an interesting data set, right? So it's just kind of different directions. But I should say, there's some rule that like being very senior and working on causality means you have to be very grumpy. So we can think of the examples of that in economics. Judea Pearl fits right in with our very senior, grumpy people who work on causality. So they all have lots of fights. You can read blogs if you want to be amused. And he's gone at it with Heckman and so on. So about whether or not this was all in Heckman or Pearl subsumes all of Heckman or Heckman subsumes all of Pearl. So, you know, for your amusement, you can read about that. But most of the applied literature that follows is pretty far from us. Okay, so of course we're good at causality. But we're bad at model selection, and we're bad at big data. Okay, so just some lessons. I think I've actually kind of gotten a little inspired by the engineering approach. So just at the MBRIO thing, I'm talking to my most structural of friends, and you know they're a little bit alarmed that I've kind of be happy to use methods that I'm not sure what their properties are. But actually, being a little bit liberated can sometimes get you somewhere. And so I think sometimes we should be a little bit inspired by the fact that their engineering approach, like rather than just stopping a literature, they're going to find something that works. And so I think that's kind of interesting, even though we don't want to go all the way there. And again, they're very systematic because they're kind of computer guys, and so they want everything to be very algorithmic. They don't want the human to have a big role. Very low-hanging fruit for us, the model selection. I'm going to spend most of the rest of the second part talking about heterogeneity, heterogeneous treatment effects. So again, I started out at the beginning talking about ending up with like 10,000 segments of advertisers running regressions for all of them. But I had defined the segments by the cross product of big, small, industry and everything. Rather letting the data tell you heterogeneous treatment effects as well as personalized recommendations. We can do personalized medicine, personalized offers, personalized searches, and so on. And then again, these specific areas I've already highlighted: recommendation systems, topic modeling, and text analysis. So causal inference. So I'm going to say a few words to kind of tie together. And again, I'm going to talk about my work. Now, I want to tell you what I think is interesting, so I started working first on the things I thought was interesting. In each case, I think we're taking a first step, but I hope there'll be lots of work that follows. So some of the problems that I would like to try to solve is that many problems in social science have a combination of prediction and causal inference. So the prediction part might be just predicting what happens as a function of all these demographics or previous web browsing or other stuff. Existing machine learning approaches don't directly apply to causal inference. That hasn't been their goal. And then, as Hito highlighted, for a lot of these machine learning methods, we didn't even know, like the most widely used machine learning method, we only kind of know as of last year whether the prediction is asymptotically normal. I mean, can you imagine like not knowing for decades if OLS can do hypothesis testing? It's kind of a crazy thing. But so, they just haven't really even cared about it very much because they had this other thing, which was mean squared error out of sample to evaluate models. They weren't interested in asymptotic normality. So some of the proposals I have is, first of all, for economics, let's formally model the distinction between causal and predictive parts of the model and treat them differently for both estimation and inference. So let's say price, I want to focus on that. That's a causal variable. I want to understand the causal effect of price on consumer behavior or whatever. I want to understand the treatment effect of this drug. That is my focus. That is the causal part of the model. And I have one set of problems about inference and estimation about that. Then there's all these other variables, and they actually, like in the econometrics textbook, they're just a big vector of right-hand side variables, but actually these attributes are different. Like I'm not imagining I'm going to change the distribution of population characteristics. I might have the whole population, for that matter, and so those are just fundamentally different in how I think about them. I'm not going to, their distribution isn't changing while I'm going to actually change the causal variable. So I have a paper with Alberto and Hito and Jeff Wooldridge that actually says, even in small data sets, that our standard errors should be different for causal variables. And the basic idea is that suppose I have all the people at Amazon, I have all the search advertisers, or I have all the states or all the counties. If I have data from a whole population, I actually know with certainty differences, effects of characteristics. Like if I have all the states, I know the difference in income between East and West. Like that's a fact. I know that for the states. I might imagine, well, you know, maybe I want to think about what the states would be next year. But if I actually have data about 1 year for 50 states, I know the difference between East and West in that data set. And if I wanted to predict the difference between East and West next year, I should get a panel data set, right? Because states are pretty highly correlated. So the cross-sectional variance between California and Maryland tells me nothing, I would argue, about what the difference between East and West will be next year. So if you calculated a standard error for the difference between the means incomes of East and West, that standard error would be based on the cross-sectional variance. But that would not have anything to do with predicting what happens between East and West next year, because East and West next year is about the serial correlation of California. If everything is highly serially correlated, then the difference East and West next year will be very similar to the difference between East and West this year. So on the other hand, if I wanted to think about the effect of changing the minimum wage, and half of the states had minimum wage high and half had low, I still, even after observing all 50 states, don't know the causal effect, the average causal effect of changing the minimum wage, because I never saw any state in both circumstances. So the problem for inference is not that I have a small sample from a large population, it's actually that I don't observe everything. I don't observe all the potential outcomes. So you actually get different answers for those things. I gave this talk in more detail somewhere else. I had a quote that was actually widely tweeted and retweeted afterwards. I love like econometric seminars getting retweeted. But anyways, my quote out of that, so the result out of that is everybody's standard errors are actually too big. So I said you should never write a paper that says people's standard errors are too small, because you'll never get cited. But if you say their standard errors are too big, you've got a shot. So everybody who wants smaller standard errors, read our paper. But more seriously, what I think is interesting about the paper is that we actually say you should think differently about inference between two different types of variables. And you actually, in the formulas, get different answers. Second, we want to develop estimation methods that so not just for standard errors, but also for how we estimate. We should treat the two types of variables differently. And so just as an example of that, I could think about building a tree to segment my advertisers, but then estimating a demand model at the bottom of the tree. Okay? So, and those were two different exercises, estimating the causal effect of price and deciding how that interacts with attributes. And so that's what a lot of our work has been on, and I'll tell you more detail about that. We've also been thinking about robustness. So we have a paper in the paper and proceedings about that, which I probably won't get to, but possibly it's in the notes. We've been looking at network experimentation. We have a paper that's just out on that. And large-scale structural models with latent variables. And I alluded to that with the news work. Okay. So just to ground everybody, the model of causal inference I'm going to use. So for the more labor folks in the audience, this is the way we're always going to write these things down. For the IO people in the audience, we can think of this YI as like demand and W as price. This is the potential outcomes model. So YI of W is the outcome unit I would have had if assigned to treatment W. Let me just make sure what I'm going to, I've got 10 more, a couple minutes before my break. So that's the potential outcomes notation. And so, again, the fundamental problem of causal inference, which is actually going to be very substantive in how we modify methods, is that we don't see all the units at the same time with different counterfactual policies. So again, we talked about the entire supervised learning literature revolves around one goal, which is I have a bunch of data on Y's and X's. I have a holdout sample. I use the X's to predict the Y's, and I see how well I do. If I'm estimating a causal effect, I can estimate it in a training sample. When I go to the prediction sample, how do I know if I did a good job? And in fact, as we know, like if I was doing an IV estimate, I would exactly not do a good job at predicting the Y's. So what do you do for the ground truth? And we're going to have a solution to that, but that's something that has not been grappled with at all, basically, in the machine learning literature. And so the units of study typically have these fixed attributes X. So I'm going to decompose my right-hand side variables into the causal variables and the attributes. And I should say, by the way, mostly harmless econometrics makes this distinction. Most other econometrics textbooks don't. Okay, so causal inference versus prediction. Let's start with that. So of course, in economics, we want to make decisions. Decisions are about allocating resources. So that's why we care about causality. Nonetheless, prediction can actually play the dominant role in causal inference in a bunch of situations. So one that Sindel Mullainathan has emphasized a lot is that they're decisions where if you know the underlying state of the world, you know what to do. So if you know it's going to rain, you're going to bring an umbrella. So all I really care about is predicting rain. Another class is that prediction is a dominant component of your estimation for causal inference. So propensity score estimation. It's just estimating the probability you get a treatment. It's a pure prediction problem. The first stage of indeterminate variables are two-stage least squares. Not for interpretation, pure prediction problem. So there we just immediately can do better by applying machine learning techniques. Predicting the baseline in a difference in difference setting. Or in a time series setting. And by the way, the one place where supervised learning has already had a lot of inroads is time series econometrics has been, because it's about prediction, has been having more interaction with machine learning in the last few years. Okay, so this paper by Sindel, and he has a paper in the Papers and Proceedings and also some other related work, has these motivating examples where all you care about is the state of the world. Will it rain? Which teacher is best? Unemployment spell length, etc. And so he writes down a little model, and he says, okay, imagine there's some state of the world. The effect of a decision on my payoff is the effect of the decision on my payoff directly, plus the, actually, I'm sorry, this should be, yeah. And then, then the second component is how the state of the world changes my payoff times the derivative of the state of the world with respect to my payoff. And Sindel says, this is actually a prediction problem because all we have to do is predict S. And he says, well, taking an umbrella doesn't affect whether it rains. This is the causal part of the problem. Therefore, causal inference, the causal part actually isn't important for this problem. All that's important is prediction. So I have a little twiddle with that, just that, actually the derivative of your payoff with respect to taking an umbrella is often, that's the treatment effect. And so that's actually what many of us mean by causal inference. Nonetheless, if that derivative is always positive, if it rains, then he's right. I mean, then you really don't care about the exact value of how your payoff changes with respect to an umbrella. All you care about is whether it rains. Okay? So he's going to focus on that aspect. And so he just has a couple of really nice examples where he says, okay, if somebody's going to die, you don't want to replace their hip if they're going to die in the next year. Replacing your hip is expensive and painful, and if you're going to die in the next year, it's just going to ruin your last year of life. So he has this approach where he uses a machine learning method to predict with 65,000 Medicare patients, 3,000 variables, whether somebody's going to die. And then he does a counterfactual where he reallocates the people who are going to die away from getting hip replacements and shows that they'll be better off. Okay? So I think this is a nice example where for policy, you could just, we had old methods, there are new methods, they do better, you could save more money and save more lives.